I think I'm going to go get started if that's okay with everyone. I do want to, I was going to avoid the 9:05 rush, but I decided it's maybe better to just get started talking. So I just wanted to introduce myself. I'm Sterling. I'm talking about Apache Mynewt. So Apache Mynewt is a real-time operating system for constrained microcontroller environments. So we are, the people who use, our users, the people who use Apache Mynewt are typically people who are running ARM Cortex-M processors and MIPS and AVR, so these small constrained microcontrollers. And it's a open source project for microcontroller environments, and it's an operating system really designed for these. So if you look at kind of old school real-time operating systems like Micrium's UCOS or ThreadX, Apache Mynewt is very similar to those RTOSes in terms of the RTOS functionality. But really the goal is to build a full operating system for these microcontroller environments. So it's not just about having a small real-time kernel, it's about having good networking stacks, file systems, circular buffer mechanisms, flash access mechanisms, a good HAL. So really an operating system effort for these small microcontroller environments. And the reason you need an operating system for microcontroller environments is that microcontrollers are actually just getting bigger, right? They're going, you know, it used to be a lot of 8 and 16-bit microcontrollers. I'm not that old, but even, 10 years ago when I started, we were using Atmega 128s, and we were trying to fit IP stacks on the Atmega. We fit a full radio meshing protocol on it, and it was a mess. Now the new chipset from Nordic, the NRF52, has 512K of flash, 64K of RAM, and can actually run a full operating system, a full Bluetooth stack, and all of the application code you need to have a single processor design. And so what that ends up meaning is that you need operating systems to run on those devices, right? If you're going to have a lot of the existing embedded stuff is a while one loop. But if you're going to have a Bluetooth networking stack running on a single chip design, you need an operating system to coordinate your application tasks along with the networking stack that's running. So you're really seeing, and you see a lot of efforts in this space. So Mbed is one of them. A Zephyr, which is, I think, presented here, is another one. So everybody kind of really sees this need. And we view it from the perspective of microcontrollers are actually becoming powerful enough to run operating systems and fit all of the functionality on these little microcontrollers, and that's why you're seeing all of these operating systems. So this talk is really going to be about why we created Apache Mynewt, what the philosophy behind Apache Mynewt is, and why we think it's cool. So a little bit about me. I founded a company, Runtime.io. Runtime with Pace right over there. Runtime.io is a cloud-based management and monitoring service. So we are building a cloud service around Apache Mynewt to do software upgrades, statistics, all of the things you would need to do to manage and monitor an operating system that you're running. And Apache Mynewt is an Apache open source project, so Runtime is in no way affiliated with Apache Mynewt except for the fact that we contribute to it. So the way the Apache Software Foundation works is that everybody contributes as individuals within the Apache Software Foundation. There is no corporate affiliation when you contribute to the project within the ASF. It's a meritocracy, best idea wins. Committers vote new committers in, and it's run by volunteers. So I have 20 years in open source. I was 13 when I started programming. People were kind enough to yell at me and tell me I was a terrible coder on the internet. And through that, I actually learned how to program. And then and most of my experience back then was in servers and in web and networking. The past 10 years, I've been working in embedded wireless devices, so little, actually smart meters, smart street lights, networking at kind of large scale. So we had a mesh network of over 20 million IoT connected devices at Silver Spring Networks. I led the firmware team that developed that through multiple iterations and generations of that product. So all the way from that little Atmega I was talking about, up to running an ARM7, up to running a Cortex-M, up to running an ARM9, and fully soft radios and DSPs. So multiple iterations of that product. And so when we went out there and we looked, and when we started talking to people, actually we started Runtime, and Runtime started the Apache Mynewt project. We started as a cloud-based management and monitoring company. And so we went out and we said, you know, there's all of these connected devices, and somebody needs to manage them, right? At Silver Spring, when we had 20 million meters deployed, we had to deliver 3 nines of reliability on that network. We had multiple, probably 50, 60 different hardware revisions out in the field running at the same time, and we had to deliver over-the-air software updates to enable new features, new protocol stacks, and in doing that, we had a lot of challenges, and so we thought we would go and build a management system for these small constrained devices. What we found was pretty much everyone we talked to, from lights to locks to wearables, was really building their own operating system. So the most common answer to what operating system do you run in an IoT product is while, right? While one, do some stuff, and return it. And it's not just the operating system, right? It's everything around that. So you're trying to get this product to market, and now you have to do a file system. Well, there's really not a good embedded file system. Yeah, you can run FAT on these devices, but that's pretty much state of the art. If you want to go to journaled file systems or log-structured file systems on these small devices, most of them are GPL, which is really bad for embedded products. So everybody implements their own flash circular buffer mechanism, their own TLV data store. Everybody has their own uses a different networking stack, typically provided by the chip vendor. So if you look at these small Bluetooth connected devices, every single one of them is a precompiled binary shipped from TI or somebody else with their own implementation of Bluetooth, each of which has its own bugs. So when you want to have multiple versions of your product and you want them to use different chipsets, each of them will have completely different Bluetooth stacks with completely different sets of functionality that are available. And so what you end up building is, when you start out, because you don't have an operating system that fits in these small constrained environments, you kind of build this house of cards, right? I have to build a configuration mechanism. I'm going to build it in 2 weeks. I'm not going to spend a month on it. And 2 weeks is, you know, generous, right? Maybe it's a week. And so you kind of build this house of cards that barely works. You ship your first product, and you're lucky enough that it's successful. And then you spend the next 10 years supporting that product and all of the different iterations of that product as you evolve it, right? Because then, you know, maybe you didn't do error correction on your TLV storage mechanism. Maybe you didn't have encryption. And so now you need to constantly add that, and you need to write code that says, okay, copy my old TLV mechanism into a new one. And so it just ends up being 10 years supporting this product that you wrote in 6 months, and 90% of the work you did was on the operating system itself. And so our thought is an embedded operating system for microcontroller environments. And what we mean by embedded operating system is all of the things that you would expect to get from a real operating system like Linux, but designed for a microcontroller environment. So we really think that in a microcontroller environment, you can actually have networking stacks and file systems and configuration and management and software upgrade and all of that functionality. You just have to approach the problem slightly differently. Something like Linux isn't going to work for you in these environments. That doesn't mean you just have no operating system or you just have a real-time kernel. There's something in between that you can actually engineer in. And so our goal is to have a full operating system for these MCUs. So starting at the base layer, we have a secure bootloader for these devices. So we've written a bootloader that can work across multiple of the different Cortex-M series MCUs. There's both a flash file system that it can access called NFFS. That flash file system is a log-structured file system on these devices. It can also just access raw flash data. So a lot of the chips we run out of flash. And because they run out of flash, they obviously can't run out of the file system, because there is no RAM to load the image into. So we support both raw flash access as well as file systems on these devices. Above that, we have our operating system kernel and our HAL. So the operating system kernel is a preemptive multitasking RTOS. It's simple. They're all simple. As well as a hardware abstraction layer. And that's where we've put in a lot of the work, right? Is how do you design a hardware abstraction layer that's efficient and easy to use, that works across multiple platforms so that you can get professional developers to use it, right? Because professional developers typically are looking for efficient access mechanisms. Reading the ADC can't block, right? However, if you look at the Arduino community, all reads to the ADC block. So how do you develop a HAL that is both efficient for makers to use, as well as something that professional developers want to use? And then how do you tie that together with the board support packages so that you ensure reuse among code, right? So how do you separate out MCU definitions from specific board definitions? How do you architect a device tree and a pin mux that works well, that isn't as complicated as what Linux has, but still allows you to support large number of microcontrollers? We've then built in statistics, logging, console and shell, so all of the, I think Pace likes to call it embedded middleware, but all of the management functionality that you need when you develop these systems, right? So how do you debug most embedded systems? It's through statistics and logging, and it's mostly through statistics. When you have networking stacks out there, you're not going to be able to log every packet that you receive. You're not even going to be able to log, 1/10 of the packets you see. So a lot of it is how do you count statistics, and how do you bring those statistics back through multiple mechanisms? So statistics can be brought back not only through the logging infrastructure and the statistics infrastructure, it can be brought back over the air through Bluetooth, over the serial port, over the console. And then how do you do configuration management and upgrade on these devices? So we built a configuration management framework, as well as a software upgrade framework. And then kind of, if you look, this side of the stack is implemented. This side is not. So the goal over time is to support IP, Wi-Fi, Thread, security, HTTP, and CoAP. We've decided to focus in first on Bluetooth connected devices. So we have a full Bluetooth low energy stack for these devices, both host and controller side of it, that replaces the soft device on these chipsets. So it's a down to bare metal, down to the radio Bluetooth stack implementation. And then there's a protocol we call Mynewt Manager on top of that, which allows you to do over-the-air software upgrades. So the way Mynewt Manager works is you can run Mynewt Manager over serial, over Bluetooth, or over any of these other protocols, and you can actually manage these devices. So kind of on the other side, I think there's two things to call out here, and the other ones are just kind of messages, but it's community-driven open source. So it's an effort of all volunteers, right? Essentially. Now, three of the engineers are paid full-time by Runtime and work on Apache Mynewt, but we don't have a decision as to the direction of the product. We have a vote. We have one vote. Anybody else who contributes to this product has a vote as an equal vote. It doesn't matter how much you pay for a board seat or what you do, what corporate governance there is. This is a project that's run by the community. And then the other thing is, and I'll get in a little bit to this because I think a lot of people have questions about how that governance works, is we've implemented a build and package management system for embedded contexts. And we did that for two reasons. One was to actually have a build system that worked across all of these different platforms. The other was an artifact of how we want to develop the product and how we want to run that community effort. So we'll get into that, but just a little bit on why a community effort here. I think what we saw, and this was prior to Zephyr being released, so this was really, when we looked at Mbed a lot. But there's really any number of efforts that are going to come out there and be RTOS efforts, right? So I think Samsung's announcing a new RTOS in 2 weeks. Now, the problem you get when you have a corporation run or control an operating system is you get an unbalanced ecosystem, right? Because you have take in the case of Mbed, an ARM run and controlled effort, where you have to actually go out and cite a document saying you'll never port it to anything but an ARM core, right? What you get is you get fragmentation. You get Intel releasing an operating system and Samsung releasing an operating system. You also end up with a scenario in which ARM controls not just the IP on the chip, but any of the expanding IP is going to be better supported in their operating system. So if ARM releases a cloud, that's going to be by default the supported option in an operating system. So what you end up getting is just a ton of fragmentation without a community-driven effort, right? You see 50 different RTOSs all out there, and every one of them controlled by a corporation because it doesn't actually balance the ecosystem of cloud providers, IP providers, MCU vendors, and users. So we chose the Apache Software Foundation. The reason we chose the Apache Software Foundation is it has a very long track record of community-driven open source. So Apache is all about how you build and run communities, and it has strong licensing and IP policies. So one of the things you don't see of a project just run on GitHub, which is a lot easier to run, is you don't have contributor license agreements, you don't have IP assignment agreements. And so what ends up happening is somebody contributed code that either was protected by patents or had something in it that was copied from somewhere else. And now you release that code and all of your users end up being sued essentially or have a risk of lawsuit. So the Apache Software Foundation has shown that they can run an open source project that takes patent and licensing policy seriously so that people can actually deploy it in products, and they have all of the big names kind of contributing to it. So EMC Pivotal, IBM, pretty much all of the major corporations have centralized on the Apache Software Foundation. So now you kind of talk, so getting a little bit into that. So Apache Mynewt users today, and this is the, hey, come work on our project slide. So what we're seeing our users today are typically people with Bluetooth connected products. They really like having an open source Bluetooth stack that can actually run on these constrained environments. They like the fact that they can remove the soft device on any one of these small Bluetooth chips. And they like, and kind of from that, they're starting to build products. And then the other is makers, right? People who want to load this on the Arduino Zero and want to actually have the ability to have more advanced HAL APIs than just what the Arduino provides. When we run on Arduino, we have multiple tasks, so you can run multiple things simultaneously. So that's what we're seeing. But we think that this is an operating system that can run eventually on industrial wireless sensor networks. That's certainly my background. Wi-Fi products, and really, who knows, right? The hope is that you get the community to take this in 20 different, 30 different directions. And because it's community driven, you have that ability to see all of the cool new things being built on it. But I think as a part of this, and this being a Linux conference, there are actually some pretty interesting problems to solve, right? Operating system schedulers is not one of those problems, right? These are embedded real-time kernels. They're really, really simple. It's not hard to write an operating scheduler. However, there's a lot of work to do on power optimization, right? How do you optimize a device? How do you take it to low power modes? How do you turn on and off certain peripherals on that device? There's networking stacks are abundant in the IoT space today. There's a new one every week. And so actually, if you want to work on open source networking stacks and wireless mesh networking, this is a good effort for you. We already have a foundation and a set of engineers who have built an entire Bluetooth stack. We're going to be working on Thread and Wi-Fi and all of these other stacks. So it's a good area to play with networking. Security is a big problem in IoT. I think everybody's heard that. Everybody said that. So there's certainly a lot of security work. There's sensor algorithms and control systems. There's a lot of areas to research it. And what makes it fun is that scale makes problems interesting, right? It's not that hard to design a power-optimized system for a single chip. But when you have to design a kernel that does power optimization for really small single-chip embedded designs, all the way up to large, fairly complicated MCU designs, and architect a system that way, then it makes it a fundamentally interesting problem. So in terms of project statistics, we've been working in the ASF since September. That's why you see that dip in code there. Writing the code since July. It's about 280,000 lines of code been written so far, so we've been writing code really fast. Some of that is chip vendor header files. And then there's initial support for a simulated platform on x86, the Nordic NRF 51s and 52s. So those are the most popular Bluetooth chips. The STM F3s and F4s, those are the most popular Wi-Fi chips, and Arduino platforms, and we are adding platform support on a daily basis. We have about 10 active contributors, and we want you. So if you join the project, we're open, we want to see contributions, we want to work with people, and that's kind of it. So I have a few more slides, but I'll probably just jump into abort them halfway through and jump into a demo. But I wanted to talk a little bit about the build and package management system, just because this really ties into one of the things we built, and it really is the core of what we're building as an operating system and as a community-run effort. So essentially, one of the interesting things about Newt, and we'll have a demo of this, is it has a build and package management system that is not Make. And so on the one side, you do have an issue where you're not familiar with the system. On the other hand, there is a lot of benefits to that. And one of the major benefits to this build and package management system is that we can actually structure the project like this. So we have essentially the concept of projects, right? And so when you create your system, you create a new embedded project. Every project can also be treated as a remote repository, where you can point to and use other people's projects. So what that allows us to do when we build this system is we have the Apache Mynewt core, which is really, eventually, right now it's everything, or pretty much everything. Eventually, it's just the operating system, the hardware abstraction layer, and the board support packages. And that's all that goes into Apache Mynewt core. And as the way the ASF is run, because it's community-driven open source, there is no concept of a maintainer. So the committers are the maintainers on these projects. So what you want to do in that framework is you want to make sure that you have a very small number of committers on your Apache Mynewt core. And actually not too many changes to the core of the RTOS itself. But you need all of these other packages in order to build these embedded products. So what you do is you then have sub-projects of that Apache Mynewt system. So Apache Mynewt BLE will be the Bluetooth stack implementation for Apache Mynewt. And if you want to include that with Apache Mynewt core, you just say newt install, and it will install the BLE stack along with the core of the operating system. NFFS is our log structured flash file system. You type newt install, and that will install that along with Apache Mynewt car. Apache Mynewt sys is logging and configuration infrastructure. So our vision for this is that there's an overall umbrella project within the Apache Software Foundation called Mynewt. There's a core of the operating system itself, and then there's a set of kind of standard libraries that we support within the ASF, and then there's whatever you want on GitHub, you can go and implement and redistribute, right? Because fundamentally, the Apache Software Foundation does come with a little bit of overhead to run it, and we want to have a set of really well-tested, good libraries that are stable and community-driven, but you also just want whoever writes something useful to be able to go up, push that out there, have people start contributing it, and then over time, as those projects stabilize and mature, they can be brought within the framework of the Apache Software Foundation. This also allows us to go broad, because when we talk about doing wireless industrial sensor networks, chances are the people who are developing Bluetooth products don't want an industrial wireless sensor networking stack to come in their default OS distribution. And people who are developing wireless industrial sensor networks definitely don't want a Bluetooth and wearable framework coming in their industrial wireless sensor project. So the Newt tool allows us to maintain this method, both to maintain our code and to maintain our community, but also to support a wide variety of application use cases on these small constrained devices. So I am going to hope that internet works and the demo works, and just quickly go through and show you that. There's a lot of other stuff there, but oh, all right. Okay, there we go. Perfect. So I've gone ahead and pre-downloaded this stuff, so if the internet's not working, we have a pre-built version of it. But so this is the idea. So what we're going to use here is a tool called Newt. So the way Newt works is, so it's a build and package management tool that gives you a couple of functions. It allows you to install project dependencies. It allows you to create a project. It allows you to upgrade that project. And it allows you to build that project, as well as clean it. It also has all of the debugging support built into it. So when we implement board support packages, we implement all of the debugging scripts for the platforms we implement. So when we support an Arduino Zero BSP, we have debugger scripts to load the images we create onto the Arduino Zero, and then Newt understands where those are structured within the BSP and provides helper functions to allow you to load and debug devices on there. The goal here is that as people and as the community maintains these board support packages, they're also going to maintain these debugger scripts and the debugging programs that come with them. Because one of the biggest challenges in actually managing these embedded products is keeping a consistent tool chain, keeping a consistent debugging framework, and having that work. And then there's a bunch of other little commands. So what we're going to do is we're going to create a new project. This is going to go out to GitHub. It's going to pull the base project skeleton, and it's going to be our new project. So what that's done is it's gone out to our GitHub account, or the GitHub mirror on Apache. It's taken the skeleton of Apache Mynewt Blinky, and it's installed it into a new project called Prezo. So if you go into Prezo, and you type tree, what you're going to see is the base, and this is usually a small part of the screen on my laptop. What you're going to see is a base project skeleton. So what you get in the base project skeleton is apps Blinky. It has a package file and a source file, which is main.c, which is the OS initialization routines, and it's the simple app that blinks the LED. You get a project.yaml file that lists the dependencies of this project, and you get a pre-canned target, which is Blinky on simulator platforms. So I have a pre-canned file for the Arduino. We have to, because of some of the license issues in the Atmel software framework, we have to distribute Arduino libraries separately. So what you see here is some canned license files, and the project file just basically says there's two repositories here. One is Apache Mynewt core. Today, Apache Mynewt core is the same as world for us. We haven't gone, being so early and we're v08 beta 2, we haven't decided to break this all out yet. And you have Mynewt Arduino 0, which are the board support libraries for Arduino 0. So it says go fetch them from Apache Mynewt core. So it says get it from GitHub, get 0-dev, which is the latest development version. User is Apache. And then there is Runtime distributes the Mynewt Arduino 0 libraries separately. It says go get those. So we're going to type newt install -v, and that's going to take some time because of the internet. Or maybe it's going to be faster than I thought. So we're going to load it both in a simulated mode and onto this little device here. So this is Blinky. So it's gone out and it's installed the core's Apache Mynewt libraries in verbose mode, and it's installed them. What it's done here is it's created a project state file. So what you've said in your project YAML is you've said, I want the latest development version. But that's not actually a real version, right? So there are real versions behind those. And project.state gives you the real versions behind those. So 0.0 or 0.0.1 of these devices, which actually map to development branches, which actually map to Git branches. So the idea here being that your project YAML is kind of your rules file for what you get. Your project state file is what makes this reproducible. So somebody else can check out your version of this repository, and they can get the exact versions you use to build this file. This is very similar to what Node Package Manager does, or any of the package management systems out there. I think the only difference between us and Node is we don't redistribute small little packages. So the OS is a package. The Flash file system or any of these things are little packages. What we redistribute is the entire project. So this project we just created could be posted on GitHub and redistributed for somebody. But we want to version collections of packages. And we want to allow people to get collections of packages versions. You don't want to just install the OS. You want the OS, the HAL, and the board support packages to all be versioned together. And you want to be able to redistribute those. And so that's why we've broken out that concept. So now if you do tree, this is always long. You'll see there's something called repos that's been created. And there you have the Apache Mynewt core repo and all of the functions in there. So we have a bunch of pre-canned apps. So BLE Tiny is an application that goes out and allows you to do Bluetooth applications there. We have a boot app, which is where we have a bootloader that works across all of these Cortex platforms. And if you go down, we have a bunch of compiler definitions. So for M0, M4, and SIM. We have our file system interface. So this is the abstract interface to the file system, not the implementation of it, but we also have the implementation of the file system in there. And it's going to go on forever if I do this. So now what we're going to do is we're going to go build this app, and we're going to first build it for simulated platforms. So the way you do that is we're going to build Blinky. And Blinky has a package.yaml file. So that package.yaml basically defines the dependencies for the Blinky app. And this Blinky app is simple, so it only depends on libsOS, hardware HAL, and libs console full. And it depends upon those in the Apache Mynewt core repository. So it basically says, go look there. That's where we're going to have libsOS and all of those. And if you looked at libsOS, it would have a set of dependencies that it depended on too. So if we go, it again has a set of dependencies. It's a little bit of a more complicated definition file, but it depends on libs shell only if the shell is specified to be present. So we're now going to go build Blinky. The way we do that is we have a target. There is a pre-canned target, which is called MyBlinky for simulator. And what it defines is the app, which is apps Blinky, along with the board support package. So those are the two roots of your build tree. you have your application and your board support package. Those two are compiled separately and then brought together to form your final image. And then it says build it in debug. So we have two compiler definitions optimized in debug. And so if we type Mynewt build, my Blinky sim, it's going to go and build all that and links it. And now if we do Mynewt run, my Blinky sim, well, you can actually run that locally. And it's switching the context of the pin. You can set breakpoints. And it will separate. So if you look at Blinky, what is Blinky? Blinky is a very simple operating system task. So everything in the operating system is a task. It's a preemptive multitasking RTOS. And what you do in the Blinky task is we use HAL. We initialize the GPIO as an output. We then get the current task. You don't need to get the current task. It's just a function you call. We increment OS task loops, and we call OS time delay for 1 second. And then we toggle the GPIO pin. There is an init tasks, which is 80 line characters, but not here. And you call OS task init. You say the Blinky task. You provide it a stack. There are 2 tasks in the operating system that run pre-canned. One of them is the idle task. So that's the task that runs when nothing else is running and that switches us into low power mode. The other is the sanity task. So that's a software watchdog. It allows you to say there are operating system buffers. There are all these concepts. So it basically allows you to have a task and say if this task doesn't run and check in with sanity within time X, or if these memory pools are more than 80% utilized for more than 10 check-ins on the sanity task, go and assert and crash the system so that you can have a software watchdog in these systems. And that's pretty much it. You then just have a main function which calls OS start, OS init, OS start, and asserts if OS start ever returns, because OS start shouldn't. So that's the core of it. What we're now going to do is we're going to now take the same thing and we're going to create a target to run this on the Arduino Zero platform. So to do that, we can do Mynewt target copy. We could create it as well, my Blinky sim to my Blinky Arduino. And now we can say Mynewt target show. So now we have an exact copy of the Blinky one. We need to set the BSP. So and I don't actually know what that's called. So Mynewt info will actually tell me what packages are available. So I look there. So, OK. And then we have to do one more thing here for the My Blinky Arduino. So there's one feature of the build system called features. And what features allow you to do is that they're symbolic names that are common across all packages that allow each of the package definitions to change things like C flags or linker scripts or any of the variables you have, right? So if you think about it, you're going to have all of these packages that are getting redistributed and implemented separately. And all of them are going to need to know whether the IP stack is present. And it's not just going to be the compiler flag of whether the IP stack is present. It's going to be, do I change my linker order, or do I add different C files because of that? So the concept of features allows you to do that. In the case of the Arduino Zero, there is a bit of a conflict in the Arduino community. So there's a difference between the M0 and the Zero Pro. One pin on the board has been flipped for copyright reasons. So here, what we're going to do is we're going to set, and if you look at that, what you can see is repos, Mynewt hardware BSP. Essentially, what the features here do is it says if the C flags, set them to Arduino Zero Pro, if Arduino Zero Pro is specified. Otherwise, set them to Arduino Zero. So now we do Mynewt target show. And we say Mynewt target set. And now we can build it. And so that goes out and builds the target for Arduino 0. I'm going to plug this guy in. You won't really see the LED blink any differently, so you all have to trust me. So it goes out, builds everything for the OS, and has built it. And now to run this on the device, you type Mynewt run. And when you run on real hardware, essentially, I've already compiled and put the bootloader on this device. So what you're doing is you're creating an image that can run. So these are the same images that you can then go and use software upgrade with remotely. They have a SHA-256. They're signed with either RSA or ECC. So you have a public key that gets burned into the bootloader, which is the firmware key. There's then a private key you use to sign these images. And so Mynewt run basically will build and compile it for you. And we're going to go and do that. Because it's already been built, it's just going to load it. It's going to call it out to the hardware. And there we go. So it's stopped on the hardware. And now we can type continue. And it will run. And the LED is blinking. All right. If you wanted to, for example, break at the OS idle task, you can do that. And it may not actually enter into it because it's already running, essentially. But we could break to HAL GPIO toggle. And there you go. So you can manage breakpoints. Everything you do here, you can then go and turn around and create images out of as you go to production. So the idea being you have your development environment, the community and everybody is supporting the board support packages, making the compiler toolchain. So all of the compiler toolchain has been Dockerized by us. So we go out and we get the latest versions of ARM GCC, of everything you need there. We've put those in a Docker toolchain. We distribute that. All of the board support packages know about that Dockerized toolchain, and all of them have the debug and download scripts for it. Because our goal really here is to have very, very good hardware support for the popular dev kits. Right? So we have an infrastructure that basically has a definition of a HAL, MCU, and BSP. So our thought is we're going to maintain a lot of the most popular BSPs, the Nordic dev kits or the Arduino products. Those BSPs rely on MCU-specific definitions. So all of the header files on the SAMD21 on this guy, which are reusable because chances are when you're developing a product, what do? You buy the dev kit. You want to get it up and running on the dev kit first. You do some testing there. And then you go and design your own board. So all you have to do is create a board support package from that. And so, yeah, I guess that's a definition of Mynewt. If there are specific questions on stuff we do, I am happy to answer them either now or afterwards. Any questions? Exactly. That's the idea, right? And you don't want to have your repository stuck with 15 different protocol stack implementations, right? There are people who are now currently porting Mynewt to run OpenWSN, right? Which is the old wireless HART stuff in industrial contexts. And if I'm going to do a Bluetooth connected product, I probably don't want 100 files from OpenWSN in my repository. And if I'm doing an OpenWSN project, equally, I probably don't want. Yeah. Exactly, yeah. And so if you were building a hub device out of this, you would include multiple of the protocol stacks all in. We share buffer management across the networking stacks. So kind of in the core, what we provide to them is essentially just a good system. We provide to them a task infrastructure and a buffer management scheme, because if you're going to run two protocol stacks, IP and Bluetooth, for example, you're probably going to want to have a single pool of, we have chain packet buffer, it's called mbuffs. You're probably going to want to have a single pool of mbuffs that both of them actually use. And so we provide buffer management and task infrastructure and locking between them, but then you can use the two separately. Yeah.
Is there a C library involved here, or is the changes going on to verify
Yeah, so we use, we can either link against newlib. We've also bundled base libc, which is a smaller version of libc, so it doesn't have float support. And that, like, newlib's printf is something like 20K of code. And so for us, where we don't use a lot of float support on these small devices, but essentially what it does is you can include base libc in your project, and if it doesn't find our implementation in base libc, it'll go back to newlib. No, I haven't. Oh, we should look at it. No, I haven't. No. Cool. Any other questions? All right, well, feel free to come and talk to me afterwards, and thank you very much.